Yeah, there we go. We're all good. So we started talking about binary trees, and we talked about the traversals through the binary trees. They're not too crazy, but at the same time, you know, a lot of them are recursive heavy. So if you're still not all that comfortable with recursion, which is not a crazy thing, you might still be struggling with a little bit. But again, all you have to do is practice, practice, practice. But now let's look at an implementation of, or I guess a very incomplete implementation of a binary tree. Okie dokie. So what are we going to want to do? Well, we can remove left subtree, remove right subtree, remove all elements, is empty, size contains find, in order, pre-order, post-order, level order. I heard a boop. So the video is so bad. Let me have a look. Is it really bad for everybody? Let me just check. What? Just kind of bad? All right, well here, let me have a quick look to see if I've got some stuff running that I could turn off to maybe... All right, maybe I just have a lot of stuff running. I'll close that. I'll close that. Close that. Close that. Ooh, CPU is running really hot though. I'll just close the extra browsers. Maybe that'll save some. Pardon me. Well, man, this poor work computer. It's so sad. I don't want to have Visual Studio open. I guess I can close this one as well. Close. All right, let's see. CPU usage is still really high, but maybe it'll settle down a bit. All right, well, let me know if it's still horrible. Otherwise, sorry. Hopefully the YouTube video's recording won't be too bad. Close 20 tabs. How do you... It's funny, I actually did have a how do you C, like when I looked up Kim's question, I did have a C++ thing open. But anyways, all right, let's carry on. So hopefully it's slightly better. So linked binary tree implementation. We'll use a link structure of nodes as our container because it'll be easier this way. And all we got to do, we got to keep track of a count to know how many things are in our tree. We'll need like a pointer to the root, kind of like the same idea with a list where we'll always have a pointer to the beginning of the list. Yeah, I just said that. And well, nodes before only had a single successor, so we're going to use them here, but we're going to like modify them a bit. All we need though is like something to hold the data, a pointer to the left subchild, or a pointer to the left child, so the left subtree, and a pointer to the right subtree. That's it. Then the data can be whatever type. So we're going to want to have it be generic. So this is what we're going to want in our binary node class. What do we see here? Well, the data of type T, whatever. And then left is going to be a pointer to a binary node of type T. Right, same idea. Then we'll have our constructors, deconstructors, and then our get left, which returns a binary node, our set left, and then our get right, set right, and then get data, set data. There. So this will be the building block of building an actual like binary tree class. Now in this week's lab, you're not actually building the binary tree class, you're just using binary nodes to build a tree, but it won't be like an actual class that you're defining. Anyways, so let's take all this, let's go here, right click, add class, binary node, yeah, okay. All right, it's pretty good. Okay, now we just need to start implementing these things. Well, let's have a look at the code here. So we got that. So what will the constructor look like? Well, I guess the default will have left and right point to nothing and then have data be 0. That's like our standard empty, boring default like node constructor that we've been using. And then one that takes data, which is basically the same, we just assign the data. Our copy constructor, just copy over all the stuff. We don't know if data is a pointer or an object, so we're just gonna have to make sure we're just copying that over and know that this might not be the deepest thing. And our deconstructor, it's gonna be rather simple. There's gonna be nothing special there. Here, I'm just gonna make this full screen and just go here, paste. Because otherwise going back and forth will be annoying. Wait, can you set data to 0 even if it's generic? Yeah, because 0 is kind of like this boring old default value. Because if you were to set this to null pointer, we might have a bit of a problem here, because what if the thing of type T isn't a pointer? So 0 is kind of like this universal nothing that we can use when we have like these like template classes. What about null? I think null is, well, let's have a quick look. Let's do this as an exercise. What is the actual value of null in C++? In CPP. The value of null is implementation defined, but is usually defined as an integer constant 0. Note, as a C++11, null can be defined as null pointer instead, which we'll discuss in a bit, because null is a preprocessor macro, so it looks like it's basically the same thing. If it's a node in the data, though, would 0 do something bad? Well, I mean, remember, this is just when it's being created. So 0 would be fine if this is of type who cares. But remember, this is just on creation. Like, we're going to want to set the, like, if this is a thing of type T, if and when we ever call set data, I mean, it's going to be something of type T, right? I mean, we used this before, weeks ago, with the other one, but whatever. Let's not worry too much about this. Okay, so I copied the constructors over. Looks pretty good. Okay, get left, set left. So this is just, this is fairly, I don't want to say straightforward, but like what we've been seeing before. Get left, okay, return the thing of like that type. Set left, void, and you just set it. Get right, set right. Yeah, and then it's going to be the same thing for data. For get, return the thing of type T, and for set, give it something of type T. Okay. And I think that's it for this class. I think that's all we need for the binary node. That's awesome. So if we want to make a binary tree now, we're going to have to, like, it's going to be a little bit, it's going to get interesting. So the constructors are going to be straightforward, right? But let's have a look at some of the interesting bits. And we're going to ignore the scary bits about like remove from the middle and whatnot, because you'll learn that next year in 255 or whatever it's called. But we're going to do a find, we're going to do traversals, and the scary bits will be studied next year. So have fun with that. So let's say we want to search the tree for a specific target. All right, so like, how do we do this? Think recursively. So actually here, if I'm going to go back and find an example of the tree. So like, let's say I was looking for F, right? If you were to go look for F, like how would you do that? Think recursively, because the recursive implementation is going to be nice, quick, and easy and simple looking. But thinking recursively, how would you do, I mean, this is basically like a search, right? Like think linear search, but of course this isn't linear. If you're doing a linear search, you start at the beginning and you go to each next thing till you get to the end. And you look for the thing. If you find the thing at any point, you found it. If you didn't and you get to the end and you still didn't find it, well then it's not there. So it's the same core principle here, but this isn't a linear data structure. So how would I go look for F or look for something that isn't even in there? So like, what are you thinking? Try to come up with some idea. You don't have to answer or anything, but try to come up with some idea. Like, how would you do it? Okay, let's go back. Okay, yeah. So searching the tree. Let's say we want to search the tree for a specific target. How do we do it? Well, we'll call the function find. All right. And it's going to take a binary node called cur and the target that we're looking for. And it looks like the find's actually going to return a pointer to the node that contains the data if we find the node that contains the data. So here's what we're going to do. If the thing that, if cur is pointing to a null pointer, then just return nothing. Because if cur isn't anything, is it the thing we're looking for? No, because cur is nothing. So that's like the base case here. If we're looking for the letter F, and the current is pointing to a null pointer, did we find F? No. So just return null pointer. Otherwise, here's what we're going to do. We're going to say, okay, if the current's data is what I'm looking for, return current. Otherwise, do a temp make a variable called temp, and do find on the left subtree. If temp comes back as null, that means I didn't find it, right? So I'm saying, okay, go look at the left subtree, and look what'll look what happens here. Geez, I've lost my pad. I'm missing it. This will be null. Temp will only be null because we're calling this function, right? Find, which is this. It'll only return null if we didn't find it, right? So if it's null, then we didn't find it. It returns cur if we did find it. So if temp is null, well, then we didn't find it in the left subtree. Thus, we should search the right subtree and assign it to temp. And at the end of the day, we're going to return temp. So at any point, if this comes back as some pointer to an existing node, that way we don't do this, we return that pointer. If it comes back false and we do this, and then find right comes back as the pointer to cur, we return temp, which is the node that we're looking for. Or if it's null, return null pointer. So this right here will return a pointer to the node containing the data that we're looking for, or null pointer if nothing is found. So I kind of want to do an example, but I don't have. Okay, so let's go back to that tree, I guess. There. Okay, think for a second here. I'm looking for F. So if I'm here, okay, I'm not null, all right? So, and A isn't what I'm looking for. Let's say I'm looking for the letter F. And A, is it the thing I'm looking for? No. Okay, then go to the left subtree and do the find. Call find on it. Okay, great. So now we're looking at B. Does B exist? Yeah. All right, is B F? No. All right, okay, go do a search on the left subtree. Okay, cool. Is this nothing? No. Is D the thing I'm looking for? No. Okay, do the search on the left subtree. Oh, okay, it's nothing there, so return null pointer. Okay, cool. So it returned null pointer. Remember, if we search left and we look and then we got a null pointer, we're going to then search the right subtree, right? So we can go here. H, does that not exist? No, it exists. Is HF? No. Do a search on the left. Okay, returns null pointer. So it's a null pointer. Do the search on the right. Well, that's also a null pointer. So we return null pointer. And then D can return to B, null pointer. Then B can do the search on the right subtree because B's left returned the null pointer. So we look at E. E exists. Is EF? No. Look on the left, nothing there, return null pointer. Look to the right, nothing there, return null pointer. So we just return null pointer, we propagate it back up to B, who then propagates that up to A. So B returns null pointer to A, meaning that we never found the F in this node's left subtree. So because of that, we're going to search the right subtree. Go to the right. Does C exist? Yes. Is C F? No. Okay, call it on the left subtree. Okay, perfect. Does this node exist? Yes. Is F the thing I'm looking for? Yes. Return a pointer to this. So C now got not null pointer back from its left subtree, meaning that it found it, meaning that we don't need to search the right subtree. So this will just immediately return temp, which is the pointer to F, to A. And then A goes, oh, okay, well that found it, so I can just return that to the calling function because someone called this find, right? So there you go. Maybe that was overkill, but whatever, we did it. I went way too far. Okay, so often when we write a function like this one here, right? When we write this function, you know, this is like the function that belongs to the binary tree class. But it doesn't have to, right? Because this function can exist like in like the file where your main is, because all it does is take this current here, right? And if you want to search a whole tree, you just start by calling this function with the root node. And you give it the target. But often it's like we will write these like helper functions that go with these recursive functions because they might do some extra like setup for us to make things just a little bit easier. So they're going to be the ones that are public, And we're going to usually make our helper functions private. Like the helper functions are more for this class to do what it needs to do, not for other people to use directly. So for example, here's my find, but it's a different find because it doesn't have the underscore, and this is going to be a public function. So what I'm going to do is, look, if I ever tell a binary tree to see if target's in it, I should not have to specify when I call this function right here to start at the root, because obviously it's going to start at the root if I'm going to search the whole tree. If I tell a tree, hey, do you contain this certain thing? I shouldn't have to be like, oh, and start looking at the top, because it should know that. So the public function find, all it's going to do is just hijack the function find and give it as the starting node the root. And remember, root belongs to the class binary tree, and it's like the pointer to the root node. So it's just going to call the helper class. And I'm going to create a binary node pointer called cur. If find ends up returning, like if it didn't find what we're looking for, it'll ultimately return null pointer, right? So if cur comes back null pointer, we didn't find the thing we're looking for. Just throw the exception element not found or something. Otherwise, find will just return the data from the current node, like the data that we were looking for. Maybe this should have been returning the pointer as well, but whatever. The way I wrote it, this is returning the actual data instead of a pointer to that data, which is somewhat silly because if you know what the target is and you have the target, you're going to get the data which will match the target, but whatever. This is just an example, no matter how contrived. Now, preorder traversal. Let's have a look at a preorder traversal where we simply print out the data when we visit the things. So here is a preorder traversal. Void binary tree, okay, preorder. But again, this will be a private function because I'm following the convention. We start with cur, or we have a cur. If cur is not null, do print out the data, then do preorder on the left, then preorder on the right. And then the helper function will just be preorder, except we call, or pardon me, the main function, the public function that we will call will just be called preorder. Doesn't take any parameters because we should just by default, if we're doing a preorder, we want to do it on the whole tree. So if I tell a tree do a preorder traversal, it's going to start at the root because it has to in order for it to be the whole tree. So this one just calls the helper class on root. Same thing with in order. Same thing. There we go. Now, you will actually see though, so in this case, I printed it out. But here, I'm doing something slightly different. So now let's look at in order, but instead of printing out the contents, let's build a string as we go. So the point of in order is to do, we're going to do an in order traversal, which we're all familiar with now. But we're going to do the in order traversal. But instead of, printing things out as we go, we'll have this actually generate a string that we can return. Actually, we won't even return it because we will just, we will give it a pointer to the string and then we'll modify that through the pointer. So binary tree in order, we'll take this string here, but it's a pointer to a string called ord and the current node. And if cur is not null pointer, do in order on the left subtree and give it ord, the pointer to the string that we want to modify. Then what you're going to do is you're going to dereference the pointer of the string of ord and then append to it the data of the current cell with a comma space just for nice formatting. And then do an in order on the right subtree, but again, passing the pointer to the string. So here what we're doing is at each time through, ord is a pointer to some string that exists somewhere. And every function call, every recursive function call will get a pointer called ord that goes to the exact same string that all of them are going to be modifying. So basically, when we call in order here on the left, ord will be pointing to a string that is already filled with the correct, with the string in order of all the things in the left subtree. Then I come along and get the data from the current node. Maybe it's like an A, I don't know. And then it's going to do the same thing on the right subtree. So this part is already done. This part's already done. We just need to append the A to it, and then append everything after to ord. And then here we'll just call in order, except here we'll create a string, give the memory address to the function, the private function and the root, and return order. Because this one now I'm designing it to return the string. Level order. In this one we'll need a queue. Which queue? Should it be array based? Should it be linked based? Does it matter? No. So level order, I'm going to create a linked binary queue called queue. Binary node. In queue the current. We've got our string here, ord. Well, queue is not empty. Cn is dequeue from it. Append the order with the data. If the left is not empty, or if it's not null, in queue the left. If the right's not empty, in queue the right. Repeat. That's it. Oh, and then I guess, yeah, we'll need to delete our queue because we're good programmers. So I wish I didn't accidentally just like scribble that out. But yeah, we in-queue the start, which in our case should be the root. And so our public function level order will just create the string, call level order on the root, and then at the end of the day, we're returning the string that we modified with all the recursive calls. So yeah, I'm just going to go over this one again, just in case, because I can imagine it being slightly confusing. What are we doing? We create a queue. We create a binary node, Cn. Really, this is just a binary node pointer, right? So I'm not even creating the binary node. I'm creating a binary node pointer that's going to just kind of keep track of the thing that we're going to be dequeuing from the queue. So I'm going to take the queue and in-queue the current. So this is like in-queuing the root. Then, if the queue is not empty, dequeue it, append to the end the data of Cn, and if Cn's left exists, in-queue it. If its right exists, in-queue it. Then repeat. And that was level order. The only thing magic and slightly different here was the fact that we're doing the string building. Now deleting. How do we go about deleting the tree? Well, if we think recursively, and also a lot of times, I know it sounds like when you're not used to recursion, it could sound like, when I say think recursively, you might say like, ugh, oh my God, it's so much more work to think recursively. A lot of times it's actually, that's actually the opposite of the case. A lot of times when you start thinking recursively, it's kind of like the lazy way of doing things. So how about this? If the tree exists, delete the left subtree, delete the right subtree, then delete the current node. There. If I exist, well, I'll have to delete everything over here. I'll have to delete everything over here, and then I'll delete myself. Yeah. So let's think. Oh, I got an extra little squiggles there. So delete tree, it's going to start with the current. So if current's not null, call delete tree on the left node, call delete tree on the right node, and then delete cur. And then the deconstructor just needs to call this the private function here on root. And if you're saying like, wait, hold on, but how do you delete the left subtree? Well, that's what the recursive call does. Because if I have a tree that looks like, let's say the tree looks like this, just a really simple one. Okay, ugh, all right. So what are we gonna do? We're gonna start here. Do you exist? Yes. All right, so delete the left subtree. Okay, so now we're here. Okay, do you exist? Yes. Okay, delete the left subtree. Okay, go here. Do you exist? Yes. Okay, go to the left subtree and go delete it. Do you exist? No. Oh, okay, so we're done. Nothing to delete here. Go to the right subtree. Oh, nothing there, nothing to do there. So now that I've dealt with the left and right for this node, I can delete cur, which is this now. So this is gone. It's weird. It's almost like, well, whatever. Then we return back to here. So now we know we've deleted the left subtree. We just need to delete the right subtree. So we go here. Do you exist? Yes. Okay, delete the left. Oh, doesn't exist. Delete the right. Oh, doesn't exist. Delete yourself. Great. Great. So now this guy's just finished deleting its right subtree, so it can delete itself. Return here. Oh, we just finished deleting the whole left subtree, so go delete the whole right subtree. Okay. Go to the left. Oh, nothing exists. Done. Go to the right. Okay. Now we're here. Go to the left. Nothing exists. Okay, done. Go to the right. Nothing exists. Awesome. Delete yourself. Return. Delete yourself. Return. Now I'm done my right subtree, so I can delete myself. Boop. All done. Again, if you're looking at this and saying, wait, what? Slow down. You're looking for a trick. You're looking for a silver bullet. You're looking for a rule that'll give you a shortcut. But there's one rule. What does the code say? Nothing in this code is magic. Nothing in this code isn't beyond the first couple of weeks of 161. Obviously, recursion seems like an advanced idea, but if you just follow the code, what does it say to do? Okay, it takes something called cur. Do you exist or not? Call this function. Okay, great. And then on what? Well, the left subtree. Okay, cool. So now cur is that left subtree. Do you just follow the code? And if you're having a hard time, following the code, it's because you don't have a sheet of paper and a pencil with you. Which one of the best investments I ever made during my undergrad is I bought a whiteboard with like the markers. Fantastic idea. And you know what's funny is it was with trees. I went out and got one once I started learning trees because that's where I stopped being able to really keep track of everything in my head easily. Anyways, there. Any questions about the binary trees before we move on to binary search trees? And I'll just grab some water. Okay, seeing nothing. Of course, if you think of any questions, be sure to ask. Otherwise, let's move on to the binary. Oh, I heard a boop, but I'm just going to open up binary. Oh, shoot. Binary search trees, because it could take a second. Binary search trees. Okie dokie. I hear the boops. Just give me a sec. Okay. Geez, PowerPoint takes forever to open. Okay. Is nobody else sweating? What are you sweating about? What? Remember, this stuff is look, we're now in the realm of non-trivial algorithms. These are algorithms where if you're expecting to sit down, have me explain it, and you go, oh yeah, it makes perfect sense. From the get-go, that's not going to happen. You'd have, if you are capable and smart enough for that, fantastic, you're in the right place. If you're not, you're normal, because these are advanced, complex algorithms, and the only way you're going to get comfortable with them is through practice. And a good place to get practice with these trees is assignment 4. Which is optional, but again, will replace your lowest mark on any other assignment, blah, blah, blah. Yeah. So if it's making you go, wait, what? Don't worry too much. Because really, will there be trees on the final? There absolutely could be trees on the final. So another great place to get practice would be playing around. Are they evergreens? I mean, no. Yeah, but assignment 4 would be practice. I know, I'm sorry. I do like evergreens myself. I can see a bunch out the window. They're quite lovely. Yeah, so, and remember, the only things here, really, when it comes to the trees are, well, the binary tree nodes, which are, those should be easy for you to implement. And the only things we really looked at were, like, the recursive stuff. This is the first time I've ever been called normal. That was awesome. Okay, well, hold on. Let's not get too ahead of ourselves here. We're all taking computer science here. So we are already by default, maybe not quite that normal, but you are normal for a computer scientist. I can say that. So there you go. That was funny though. Well done. All right, yeah. So yeah, just it's practice, and it's the recursive stuff, which a lot of people, they're struggling because they're looking for those tricky things. And a lot of times too, people are like, oh, recursion, that's big, bad, and scary. No, that's nonsense. Just follow the rules. Just take your time, follow the rules, and you'll be a wizard. All right, time for binary search trees. Oh, another boop. Post recursion memes in the Discord. Okay, yes, do that. I recommend it. Yeah. Anyways, binary. Wait. Yeah. Okay. Wait. What? This should be binary search trees. There. More boops. What's everyone booping about? If we were wizards, then we wouldn't be very normal. But you'd be a normal wizard. Look, stop trying to apply logic here. That's a huge mistake. 7-zip wizard. 7-zip install wizard. Okay, come on. We gotta stop now. These are pretty good jokes, though. All right, binary search trees. So what are binary search trees? And we're going to look at a basic incomplete definition of one, or implementation of one, because again, there's going to be some complexities and whatnot around how we go about implementing all that. And the binary search tree is going to be we can use that as an interesting foundation for building an ordered list that will seem a lot better than a regular ordered list. Okay. Binary search trees. A binary search tree is a binary tree where all values in the left subtree are less than the value of the root, and all values in the right subtree are greater than to the values in the root. This definition, though, do note that this definition does not allow duplicates, but if we wanted to enable it to have duplicates involved, we can do something like, well, all values in the right subtree are greater than or equal to the value in the root node. Then we know that we can have duplicates. So here, if we look here, this is not a binary search tree. Let's have a look. The rule is, here's the root. Is everything to the left of this root less than it? Well, 7, 9, 3, and 8, they're all less than 10, but let's keep going. Is 7. Is everything to the left of this node less than 7? 3, okay, yes. Is everything to the right of this node greater than 7? Well, we've got the 9 and the 8. I know 8's less than 9, which is good because it's on the left. And 8, though, is to the right of 7 because you have to go right through its right child to get to the 8. But then once we go over here, well, 15, 11, and 16 are all greater than 10. But see how 16 is within its left subtree. Therefore, it's violating the rule that everything in the left subtree must be greater than, less than the root. Now, here, let's have a look. Well, we've got 8, okay, 5, 9. Okay, this looks pretty good. 14, we got 26 here. 19, 20. Okay, this looks good. This looks like a nice binary search tree. Wait. And then what's this one here? Okay. Now, neat facts about a binary search tree. What is the leftmost node in this tree? Well, it's 3. And what's interesting about 3 in this example? Someone type in the chat. Let's have a look. Smallest. Yes, it is. Now, this is just one example, but I wonder if that's going to be true in all cases. Like, what if, let's think, can that be generalized? Well, I mean, Johannes seems to think it can, but let's think about it. Well, actually here, the node to the left, okay? If everything to the left of it must be less than it, right? Anything to the right must be greater. So 3 we know is the smallest, but like imagine we had the 7 here and the 3 didn't exist. Because everything that must be less than 7 that exists within this tree, if it is a binary search tree, everything in the tree that is less than 7 must be to the left of 7. But nothing is to the left of 7. Therefore, 7 must be the smallest number, right? Let's generalize it. If everything to the left... Oh, let's hear it. Can you explain about 7 and 8? What do you...
Like how if everything must be to the right of it that's greater than it, but 8's in line with it.
No.
Like what?
It's in its right subtree. It's not in line with it.
Okay.
Yeah, so the 8, because 8 is in 7's right subtree, and this is the whole subtree. I mean, it's a small one. We're good. It's not in line. I know it looks like they're lined up, but that's just a coincidence of the formatting here. Yeah. So if any number here, the leftmost node, if the leftmost node had anything less than it, it must be in its left child. But if its left child doesn't exist, like if its left subtree doesn't exist, therefore there cannot be anything less than it. Now, what would be the rightmost node here, which is 15? Well, if anything was bigger than this node, the rightmost one, there would be something to the right of it. But nothing's to the right of it. Therefore, there must not be a single thing in this tree that is bigger than this node. Huh. That's kind of neat. So a binary search tree is a special case of a binary tree, right? So like all binary search trees are binary trees. But not all binary search trees, or pardon me, not all binary trees are binary search trees. Boop. So why couldn't there be, say, a 2 in the left of 12? Whoop. Well, you mean here? Because 2 is less than 10, and then it would break the rule. Got to be bigger than 10. Yeah, that's exactly it. Because 2 would be in the right subtree of 10, but that's no good because it should have been over here. Yeah. See, there we go. We're in great shape. So it'll have all the operations of a binary tree. Inheritance might be handy here, but it will also have a few special operations like add. Because remember before with a regular binary tree, it was with a regular binary tree, I said add, and the question was like, well, where? Well, the benefit is with a binary search tree, if I do an add, it actually, like, we now will know where. Because let's say I go back here, clear all. If I go back here and say, let's add the number 2, where should it go? Well, if I'm looking here, I go, well, because it's less than 10, it needs to go to the left. It's less than 7, needs to go to the left. Less than 3 needs to go to the left. Well, there's nothing here, so I can just make the 2. And now let's say I go and add the number 6, okay? No, 5. Let's add 5. So 5, well, okay. No, 5, gotta go to the left. 5, oh, 5's greater than 3, so the 5 needs to be here. Now if I go add 4, well, okay, 4 less than, greater than, less than. So whenever we add something, because the order has to be preserved, we will be able to find where it belongs in this tree. And remove, if we remove something, it must maintain the ordering. And remove max will be easy and remove min. Although, will it? Because what happens? Like, let's say, if I remove the 7, that's an interior node. I guess I'm going to have this point here or something. And same with max. I guess I'll have to have that like get promoted. But if I say remove like 9, or if I said remove 10, we got a bit of a problem here, right? A little bit of complexity, I suppose, when it comes to the removes. So the special ordering lets us search for things within a tree very efficiently. Because let me put it this way. Shoot, I wish I had a nice big book here. Let me put it this way. If it's not painfully obvious already, I'm looking for page, you can see this book right here. And we'll end with this because why not? Here's this book. Okay, see how thick it is? It's big. And there are, let's see, about 800 pages in this book. All right? So if I'm looking for page 400, okay, where am I going to start? Am I going to start on page 1 and go, okay, is this 400? No. Am I going to? No, that's not 400. And so on and so on and so on. What am I going to do? You'll go to the middle-ish. Okay, and what do we got? We got page 328, 329. So that's where I am. So this is page 329 over here. Knowing that I'm looking at 329, should I look over here? This is page 328. All the numbers in this side of the book are less than 329. So should I look over here? No, that's a dumb idea because I know that the number's not going to be there if there's an ordering. So I've basically thrown away half the book. I've thrown away half the things I need to look at. Isn't that amazing? Where before, if I started at the beginning, I'm going to have to go like page by page and look at all the pictures and everything in there. But because I know, well, no, 400 is bigger than 329, so I should look on this side. So I don't know, maybe I'll go here. 503 and 502. Well, I've gone too far. But if these are all bigger numbers than 400, I mean, why would I care about looking? I can just go, I don't know, somewhere between the two. 431, well, I should go here a little more. 407, oh, we're getting there. We're getting there. 370, oh, I went too far. Point being, we can keep throwing away like half of the stuff and we can narrow down, right? Do you remember last semester, for those of you that took 161 with me, I had you guess a number between 0 and like 4 billion, and I promised you I would get it in less than 32 guesses. Or less than or equal to 32 guesses. And I did. I did. It happened. I mean, if I were doing a search for, like if we were to play this game, I'd say, okay, a number between 0 and 4 billion. If I say, okay, is it 0? No. Is it 1? No. Is it 2? No. That's going to take a while, right? I'm going to have to count to 1 billion. Well, that sucks. Or I do this fancy idea of like, okay, well, I'm going to start, is it 2 billion? Higher or lower? Oh, it's lower. Okay, is it 1 billion? Higher or lower? Higher. Okay, 1.5 billion. Lower. 1.25 billion. Lower. Okay. 1.171, whatever. Point being, I just keep kind of like having until I narrow down where I need to go. And that's the magic that we're going to see with the binary search trees. But we will end here for the day. And yeah, I hope you all have a wonderful weekend. And I'll see some of you in lab today, and the other half I'll see you on Tuesday or Monday if you come to stream, of course.